Alright, hello class. In this video we're going to be talking about the calculus of vector-valued functions, or as I like to shorten it down to just vector functions. And I think a lot of this will feel very self-explanatory. So let's start with limits of vector functions. And when we have limits, we have derivatives. So we're not going to spend a lot of time on the limits because we want to get to the derivatives. But when you have limits, you have derivatives. And where you have derivatives, then you can start talking about things like velocity, acceleration, stuff like that. And when you have derivatives, you also have integrals. Okay? So all right, let's take a look at what we have here. All right, so with our vector-valued functions here, since they are a function just of a single independent variable, we can take limits how you would expect, right? If I'm taking the limit as t goes to some value a, that's the same thing as taking the limit of this whole vector-valued function. Okay, so shift that over there, and it would be the same as just taking the limit of this. Now, it turns out that the limit can jump into the vector component-wise. And the reason for that, actually, I think the quickest way to explain it comes from the fact that our vectors can be represented in an algebraic term. That is that the vector x, y, z is actually x of t I plus y of t j plus z of t k. And since we can write every vector in this form, there's nothing stopping us from distributing the limit across this sum. Since we can write every vector as a sum, this is really just going to be the limit as t goes to a of x of t times I plus the limit as t goes to a y of t j plus the limit as t goes to a of z of t k. So this is actually the vector limit t goes to a of x of t, the limit as t goes to a of y of t, and the limit as t goes to a of z of t. Okay, and that's really all there is to taking the limit of a vector-valued function. Okay, so just to give an example, if I wanted to say take the limit as t goes to 0 of, let's say, this vector-valued function here. Okay, let me actually change that. Say we're taking the limit as t goes to 1 of t squared minus 1 all over t minus 1, comma e to the t minus 1. So we would just approach this how we normally would. It'll be the limit as t goes to 1 of t squared minus 1 all over t minus 1, and the limit as t goes to 1 of e to the t minus 1. Well, this is a 0 over 0 case, so what we typically do is either factor and cancel, use conjugating factor, maybe use L'Hopital's rule. It just depends on what you're most familiar with, but I'm just going to factor and cancel this since this is a 0 over 0 case. So this will be the limit as t goes to 1 of, this will be t plus 1 times t minus 1 all over t minus 1, so the t minus 1's cancel. And here we can just plug in the 1 because e to the 0 is just 1. All right, and then we're going to get now the limit as t goes to 1 of t plus 1, comma 1. And when we plug in the 1 now, we just get the vector 2, 1. Okay, so the question might be, well, what does this actually mean exactly? It just depends on whatever this particular vector valued function looks like. So let's see. All right, so here in blue is actually the graph of the vector valued function from t equals 0 to t equals 2. All right, and it turns out that if you plug 1 in exactly, so if we jump back to here, if we were to plug 1 in exactly, we would get an undefined point here. Well, here we wouldn't, but so what that actually means is we have a hole, okay, in the vector valued function there. So the continuity ideas pretty much stay the same. And so when we talk about the limit, what's happening is as we get closer and closer and closer from, say, this side here, we approach that point. Okay, and then let me alter my thing here. We can also come at it from this side. Okay. Okay, so now let me just show what t is when I'm doing this. So here, when t is above 1 and we're coming down closer to it, we can see that point is getting closer and closer and closer to that hole. All right, and then as we come up this way, we get closer and closer and closer to that hole as well. And then that particular value is, of course, the vector or the point 2, 1. Okay, so this is how vector valued functions work as far as limits are concerned. Okay, so now that we have that idea that the limit of a vector valued function you can just take component-wise, we can then now actually define the derivative, because all the derivative is, say f prime of x, is a limit. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. So that means if we have a vector valued function, let's say r of t equals x of t, y of t, and z of t, okay, its derivative is just going to be the limit as h goes to 0 of r of t plus h minus r of t, this is the vector, all over h. So that's just going to be the limit as h goes to 0 of, well, it will be the full vector. I'm going to bring the h in. So it will be the vector valued function x of t plus h minus x of t all over h, comma, y of t plus h minus y of t all over h, comma, z of t plus h minus z of t all over h in each one of its components. But now we can move the limit in, and when we do, this actually just becomes x prime of t, comma, y prime of t, okay, comma, z prime of t. Okay, and that's really all there is to it. If you want to take the derivative of a vector valued function, it's just the derivative of each piece. All right, so if, let's say, just to look at an example here, say we have a vector valued function, r of t is e to the 2t times cosine t, comma, the square root of t squared plus 2, comma, tangent of the natural log of t cubed plus 2t to the fifth. So this is probably where we might want to instead use the IJK notation, okay? But r prime is just going to be, well, we'll take the derivative of the first component, which is going to be a product rule, right? Since we have two things multiplied together, so product rule would be derivative of the first, so that would be 2e to the 2t times cosine of t. Then plus the first guy left alone times the derivative of the second, and that's going to be negative sine of t. So let's just make that a minus sine t there. Okay, and that is going to be our x component. So what I'm going to do is I'm going to write it with the I. Okay. Just because I probably will go off the screen if I try to put it all in the bracket notation. All right, then now we'll take the derivative of the second component, and that's the square root of stuff. So this is a chain rule. So the square root of stuff, well, when you take the derivative of the square root of u, that's always u prime over 2 square root u. Okay, so here it's going to be always, it's 2 times itself, right? So that's always in the denominator of square root of stuff. And now we just put the derivative of that stuff up top. So the derivative of the stuff will just be 2t. And the 2's cancel, and then I'll just say that that's the j component. And then down here, we will do the third one. Now this is a chain rule within a chain rule within a chain rule. Oh my goodness. Well, remember, we just take it a step at a time. The derivative of tangent of stuff. So I always do this. I just kind of forget that all this stuff is in here. I just know that this is tangent of stuff. All right, so the derivative of tangent of stuff is secant squared of that stuff. And then I start worrying about time multiplying by the derivative of the stuff. Okay, so bring that back. It's going to be secant squared of the stuff. So I'm just going to copy this down. So that's the natural log of t cubed plus 2t to the fifth. Okay, now I'm going to start multiplying by the derivative of the inside. Well, the derivative of the inside is now natural log of stuff. So the derivative of the natural log of stuff, let me just forget about the stuff now. It's just natural log of stuff. So that's going to be the derivative of that stuff over itself. Okay, so be the derivative of this stuff, so that will be 3t squared plus 10t to the fourth over the stuff. So that's t cubed plus 2t to the fifth. And then that is our k component. Right, and this simplifies a bit because we can factor a t squared out of both the top and the bottom. Okay, so when we do that, the t squared cancels here and leaves a 1. It will take 2 out of here, and it will leave a 3 here. So if you don't follow that, just factor t squared out of both the top and the bottom, or a better way might be to just factor the top and bottom completely. So you would have t squared times 3 plus 10t squared. And on the bottom, you would have t cubed 1, and then times 1 plus 2t squared. Okay, and then you'll be left with a t down here when you are finished canceling. Okay, we don't have to do that, but I'm just saying we could if we wanted to make this look a little simpler. All right, so the final answer will look something like this. Okay, so we'll get e to the 2t times 2 cosine t minus sine t I plus t over the square root of t squared plus 2j plus secant squared of this natural log of t cubed plus 2t to the 5th times 3 plus 10t squared all over t times 1 plus 2t squared k. All right, so as you can see from this, other than the fact that we just need to make sure we keep the I, the j, and the k isolated, that's really all there is to it. We just differentiate term by term. Okay, so the true question then would be, what does the derivative actually give us? All right, so all of our previous rules still hold. Okay, all the previous rules still hold. So chain rule, product rule, quotient rule, etc., all still hold. So the big question is not necessarily how do we calculate the derivatives, because if you've gotten through Cal 1 and Cal 2, you know how to do that. And now we're just doing it, say, 3 times in a 3-dimensional vector. The bigger question is, well, what is r prime? Okay, and it turns out that everything we've learned before still carries over as well. That if r is the position or trajectory of an object, r prime is going to give us the velocity, and r double prime is going to give us the acceleration. All right, so put simply, if r of t gives the position or trajectory of an object at any point t, then v of t, which is the derivative, is the velocity vector. And a of t, which is v prime of t, which is r double prime of t, is the acceleration vector. So what that means is, if you are talking about, say here's your r of t. This gives us the position at time t, right? So say maybe at t equals 0 we're here, t equals 1 we're here, at 2 we're here, at 3 we're here. R prime gives us the velocity vector of the object at each time. And what's actually fascinating about it is, if we just look at it in standard position, it's not really that interesting. However, if we look at the velocity vector at the point itself, one, it's going to be tangent to the curve, but even more importantly, the magnitude of this vector, so this would be, let's call this v sub 1, or v naught, v sub 1, v sub 2. It turns out that the magnitude is the speed. So the magnitude of, say, v naught here is the speed, and the direction of v naught is the actual direction the object is facing as it's traveling. So if this is a bug walking along the board, okay, or walking along your sheet of paper, at this moment, this v is the direction that the bug is facing, and the length of that vector is the speed of the bug at that moment in time. Okay, so here I've just summarized that a little bit. So I find it easier to actually look on a nice accurate graph, so I'm going to jump to that right now. All right, so the actual example we're going to look at with our graph is this vector valued function here. T squared minus 1 in the x component and t cubed minus t in the y component. And we're going to let t range from -1 to 2 just because. There's nothing set in stone there. Okay. Now, our velocity vector is just going to be our r prime. So that's going to be the vector 2t, comma, 3t squared minus 1. All right. So now that we know what example we're talking about, let's jump to the graph. Actually, sorry, I meant to say we're going from -1.5. Okay, so I've charted out the path here. And here is as time goes on. Okay, we see I've named this S for position, but you'll notice that it actually starts to slow down here. This is the same time step each time, okay, and then it starts to speed up as it goes along the path. Okay, so it slows down, okay, and then speeds up. All right, so also, here is the vector r. Now, this is just to remind us of what the vector r, that position vector, is actually doing for us. Remember, it sits at the origin and points to where the object is at any given time. Okay? All right, now I want to just look at the derivative of r, okay, the vector v, and to show that at the, say, in standard position, it doesn't really show us very much. Okay, so here in orange is the vector v at each time, and as you can see, centered at the origin there, it doesn't really tell us very much. Okay, so let's instead, at each time, let v have its starting point at this point S as it travels around. All right, so here we go. Now I've moved the vector v, I've put it in red, and it's starting here at our point S. So now, hopefully it's a little easier to see that what the vector v is doing is it is pointing in the direction that S is traveling, and its length directly corresponds to the speed of S. Okay? And here at each time value, we're seeing the velocity itself, the actual speed that the object is traveling in, and we can see from just the numbers that it decreases down to be less than 1 around here, and then starts to jump back up to around 10 up around here. Now if I get rid of the path, without the path, what v is doing is showing the direction of travel and the speed. Now this does bring us to a concept that we do use quite a bit, and that is the unit tangent vector. Okay, which is usually just called capital T, and it's r prime over the magnitude of r prime. Or you could say it's v over the magnitude of v. Okay, so all this is the unit vector in the direction of v, and so what t does is it basically just gives us the direction itself, okay, of the direction that the object is traveling in itself without the magnitude or without the velocity. So in this case, the speed is going to be the magnitude of v, which will be the square root of, in this case, 2t squared, okay, plus 3t squared minus 1 all squared. Okay, so we could simplify this. I don't know if it's actually going to be all that useful, but I will just say that this is 4t squared here, and I'll leave this one alone because I don't think that this will simplify all that much. So this would be the speed. This would give us the speed at every second, and actually that's what I plugged in here. That's what this is spitting out, is for each t value, it's using this formula to give us the speed. Okay, and that means that the unit tangent vector at t, okay, is going to be our vector v, which is the vector 2t, comma 3t squared minus 1, all over the square root of 4t squared plus 3t squared minus 1 all squared. Okay, so let's take a look at what capital T looks like, and you'll see what I mean by saying that all it does is give us the direction at each time. The only thing you got to worry about is if the velocity is ever 0, this isn't going to work. Okay, so any place that your point stops, you're not going to get a tangent vector because you're not going to get a velocity vector, because if your object actually comes to a complete stop, well, then there's no direction that it's traveling in, right? So it'll just be undefined here. All right, so here in orange is the unit normal, t, and as you can see, it matches the direction of v at every point, but has just length 1. Okay, and if we drop v, we can see that what t is doing is basically just telling us the direction that our object is facing at every time little t. Okay, now this is very helpful if we don't know what the path is, but here we do know what the path is. But even if we know the path, what capital T is telling us is just the direction of travel, and what v tells us is the direction of travel and the speed at which we're traveling. Okay, so both of these concepts are extremely important when it comes to calculus and detailing how, say, if this is a bug, how it's traveling, say how fast, what direction, etc., as it changes its position over time. All right, next, we haven't talked about yet is the acceleration vector. So A is v prime, which is r double prime. What I want to mention here, notice that I'm dropping the of t's. You'll see me do that a lot, especially, this is something I do commonly in Calculus 3, just because eventually our inputs, if we put parentheses for every little thing, it would get really out of hand really fast. So often I drop that just to make everything more readable. Okay, so, all right. Now the acceleration vector, now we just differentiate again to get 2, comma, 6t. Okay, and so now let's take a look at this graph as we go forward. All right, so here's the graph, and as you can see, we have the acceleration. And one thing to note there, remember that vector was always 2 comma something, and you'll notice that in the x direction it is always pointing to the right by 2 units. Okay, so that gives us the acceleration at every point. So hopefully it's become fairly clear how powerful this tool can be in dealing with physics problems or other physical problems. All right, so now that we have derivatives, we can talk about integration. And it turns out, since all integration is the reverse of differentiation, right? If we're going from r to r prime using derivatives, well, then we go from r prime back to r using integration, right? So it turns out then if we want to integrate r, and let's say it's just x of t comma y of t, well, if all we want to do is integrate, well, we just integrate term by term, okay, component by component. Okay, so it works the same way. You just do it in each particular piece. So what I want to do is, again, it's more about, to me, how this applies, what it gives us in a physical sense. All right, so in that spirit, I would like to look at an example to show you how powerful these tools can be in comparison to the things that we've talked about before. Because with Calculus 1, when we were looking at, say, the trajectory, let's say something was thrown into the air, okay, what this was modeling was literally just the height, okay, say the height versus t. All right, and which is kind of limiting. So when it comes to vector valued functions in 3-space, we can actually model what's going on in 3 dimensions. All right, so let's check out this example here. Let's suppose a cannonball is fired at the origin with initial velocity v0, which is 5, 5, 10, and I forgot to put it here, but that should be meters per second. So what this is saying is that it's fired in the x direction, 5 meters per second. So if we think about this on a xy plane, it's going 5 meters per second in the x direction, 5 meters per second in the y direction, and 10 meters per second in the z direction. So that means it's actually firing in this direction with this sort of initial velocity here. Okay, so we'll take a look with a better graph here in a minute. Okay, but given that, we want to find the trajectory of the cannonball if the only acceleration affecting the cannonball is gravity. So I would imagine that without anything else affecting the cannonball, what's going to happen is it will just continue to travel in this along this diagonal here over the xy plane, and eventually will hit its apex and then start to decrease again. And since there's nothing else affecting this, it should just go up and down. But however, unlike over here, where we're talking about a one-dimensional idea, this is cruising over the diagonal. Okay, so if the only acceleration affecting the cannonball is gravity, that tells us that our acceleration vector should be 0, 0, negative 9.8, and this would be in meters per second squared, right? Because if we have no other acceleration, well, gravity is only going to be affecting the cannonball by pulling down in the negative z direction. If we are assuming that, and we are, that the xy plane is the ground and z is our vertical axis. Okay? So given that, Now, when we go to our velocity, which should just be the integral of our acceleration, well, it's actually not that bad. Integral of 0 is 0, integral of 0 is 0, integral of negative 9.8 is negative 9.8t. However, the only thing we don't need to forget here is we get arbitrary constants, and we're going to get one for each component. Okay, we get one for x, for y, and for z. Okay, and so from here, I'm going to move over to orange now. V of t, okay, is going to be a constant, and negative 0.98t plus a constant. All right, now from here, this is where we use that initial velocity. If the initial velocity is 5, 5, 10, that's telling us that v of 0 is 5, 5, 10. But now that we have an idea for the function itself, that means this is going to be cx, cy, and that goes to 0, cz. Okay, so that actually tells us what our constant values are. Right? So this tells us that vt is going to be the vector 5, 5, negative 9.8t plus 10. All right. And now we can integrate again because r is going to be the integral of v. Okay, so it's going to be the integral of 5, which will be 5t, plus, now we need arbitrary constants again, so I'll call them d. So d sub x, then it will be 5t plus d sub y, and this will be negative 4.9 t squared plus 10t plus dz. Okay. All right, so, and then once again, we're going to solve for our arbitrary constants. Now we're firing this from the origin. So if we fire it from the origin, that's 0, 0, 0. So r of 0 should be 0, 0, 0, which implies that dx, dy, and dz are all 0. So our position trajectory vector valued function is 5t, 5t, and negative 4.9t squared plus 10t, and that was also a plus 0 there. So this is our trajectory function. So now let's go to the graph and see if that actually lines up with what we would expect. All right, here at the graph, I've graphed the initial velocity here. Okay, here's v naught. And if the cannon is fired with this initial velocity from this trajectory function we just calculated, here is that trajectory function r. And then down here, I'm basically showing the projection, the shadow of the function. Okay, so as we can see, this actually does seem to make sense. So all these sort of physics-y type things we've been learning about in Calculus 1 and 2, and maybe your calculus-based physics and whatnot, well, say that that negative 4.9 t squared, whatever, that probably looked very familiar. That's just the height. We can actually affect what's going on in any of the components that we want. So we could apply, say, wind speed here and have it affect the cannonball, and we could throw in all sorts of different things. But I just wanted to show this to show that just with this new tool that we've established, we've actually gotten a much more accurate tool for describing motion in space. All right, but the integration thing doesn't have to be application-based. We can just take integrals like we normally do. Say, for example, if I want to calculate capital R, which is the definite integral of little r of t dt, we can do that. It's just going to be the integral of the first term. Don't forget my dt here, comma the integral of the second term. Okay, so in this first component, this is going to be a u substitution. Our u would be negative t cubed. And I'm going to do a quick u substitution. If you're not familiar with quick u substitution, if you didn't take me for Calculus 2, there's a video in the Calculus 2 playlist. If you go there on my YouTube channel, there's a description of what quick u substitution is and a lot more examples than we'll do here. But basically, we're going to leave the t squared alone. Then we're going to integrate e to the stuff like we normally would. So e to the stuff, it's itself. And then we divide by the derivative of the stuff. So this will be negative 3t squared. And this only ever works if the leftover t squared up here thing cancels. And you'll notice I'm not putting the plus c yet. We'll do that in just a second. And then the integral of 1 over t squared plus 1, that's going to be tan inverse of t. All right. So then I'm going to put plus c1 plus c2 in its own vector here. Okay, so it turns out capital R is the vector negative 1/3 e to the negative t cubed, comma tan inverse of t. And we can actually call this vector just the vector c. Okay, so this is something I see a lot of students mess up in this particular section, is forgetting to put that plus c. All right, don't forget about it, because there are quite a few examples out there where it's going to make a big difference that there's that arbitrary constant there every time you integrate. All right, that is our introduction to calculus of vector-valued functions. That should be enough to get you rolling on the homework, and I will see you all in the next video.